Okay, so we were talking about limits. Like I said, the limit stuff can be a little bit confusing, but the main gist is you're seeing, okay, as my graph or whatever goes to infinity, or as far as I can go to the right, what's happening with that graph? Is it going where it's like approaching a number and getting really, really close to it and it's, never going to touch it? Or is it doing something different where, it goes up forever or down forever or whatever? So the two things we called it like convergent and divergent. So like if it did have a horizontal asymptote, so kind of like this, where it's getting really, 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 really close to zero but not crossing it, that would be something that would be convergent because it's converging to a specific number. Anything else would just be categorized as divergent, and we kind of talked about like how that could be going to like infinity or negative infinity, or it could be going to, or do they just call it like does not exist? And again, I don't care which way you write that. The book's got it as does not exist, but whatever. I don't care which way you do it. So this limit for harmonic sequence property, so it says there the limit as n approaches infinity of 1 over n is always going to be 0, and then that's the limit of the harmonic sequence would be 0. We talked about this a little bit on Friday. So how that works is if we have an equation like this where it's 1 over n, we know that we can never divide by 0, right? So if we can get this bottom to be where it equals to 0, that's going to be a value that doesn't work, okay? So if n can never be 0, what's going to happen there is our graph is going to get really, really close to 0 because it keep getting smaller and smaller and smaller, like real small decimals, but it could never actually be 0 because we can't divide by 0, okay? And that has to do with the asymptote stuff. So now what we're going to do is we're going to kind of build off of that concept and kind of do some other stuff. So like I said, the properties of limits and constraints is in your example packet. So instead of having you write all of those out, they're just in this packet here. So that's the one that they're talking about here, properties of limits and constraints. So there it just says if you've got some constant value k, so like, a 5 or a 6 or something like that, and then some sort of other, sequence, or not sequence, equation or something like that here, like a sub n or whatever, if you take whatever your constant is here, so this is your constant k, if you've got a limit that is that constant, it's just always going to kick out that value. So if it said the limit as n approaches infinity of 5, it will always just kick out a 5, okay? Then what you can do is you can use some of these other properties here if you know what that letter is for k, and you can either, if it's a problem where you could add them or subtract them, multiply, divide, whatever. So if you can figure out what the limit of each individual part is, you can then take and add those together or subtract them or whatever you need to do with that, okay? And I'll kind of show you that on the thing that we're going to look at here. So on page 517, I'll get the picture up here. What they've got is they've got a similar equation to that harmonic sequence where it's the limit as n approaches infinity, that 1 over n, that's that same harmonic sequence, and then they've got it as plus 2 there, so it's kind of similar to like this one here where we had some sort of formula or something, and then we had a constant of like plus something, so it'd be like plus 2. What you do is you just find the limit of each of those things individually, so like the limit as, the little equation or whatever approaches infinity, and then whatever that constant is, and you just add them together. So how that works here is our limit as our limit as n approaches infinity of 1 over n would be 0, right? Because that's that same as this graph here, but then it's plus 2, so you would just take both of those and add them together, so 0 plus 2 is just 2, so the limit there would be 2. Okay, now how that looks in a graph is this picture that's here. So that's kind of the graphs that I was just talking about. So this is our normal harmonic sequence one, and then this is the one that's plus 2. Well, isn't that, if we add 2, doesn't that just shift the graph up 2 spaces? So if our limit was at 0, and then we just take that graph and shift it up 2 spaces, wouldn't that just make our limit 2? Because now it's approaching that line, but now it's just approaching 2 instead of 0. That's kind of how that concept works. So if it was subtract, it would just be, instead of raising it up, it would just be going down, okay? But it'll always kind of follow those similar patterns. So that's what that's talking about. Now our examples, like I said, they're going to be a little bit all over the place because I added some extra ones into our packet. So does everyone have this like little extra sheet here that I kind of scribbled on a piece of notebook paper? The A ones, basically, I just took some of the examples and made more examples with it, so we had a lot of examples to kind of look at. So when it says like 1A or whatever, that's just these ones on here. So what it wants us to do here is it wants to find a limit for this sequence. And we've got our sequence as q sub n is equal to 3n plus 2 over n. So what I'm going to do is I'm going to try to manipulate this in a way that I can find some individual limits of this. So like here, if I'm trying to find the limit of like each individual part here, I would go and I would split this up to be like 3n divided by n, and then the 2 divided by n. So I'm just going to switch this to where it's 3n over n plus 2 over n, okay, because that doesn't change our value at all. All that does is just kind of, manipulates it a little bit in our favor. The reason I do that is because here, if this is 3n over n, couldn't those kind of just cancel out and get that down to a 3? And then here, this would just have to stay as 2 over n. What happens here is the 3 is like our constant, so if I was just finding the limit of just this 3, so if it was like the limit as n approaches infinity of that 3, if it's just that constant value like we talked about, that just kicks out that same number that it is. And then here, if I'm finding the limit of this guy, so it would be the limit as n approaches infinity of the 2 over n. What happens here is if this is divided by n, even though the top's not 1 anymore, can't my bottom still not be 0? Yeah, so don't you think that that infinity is, or that as it approaches infinity is still going to kick out a 0? Should, right? So what happens there is that one's going to kick out a 0, and that's happening because, I'll write a little note here, it still approaches 0 because we still can't divide by 0. Okay, so it's the same concept, even though it's a 2 on the top, we still can't divide by 0, so it still approaches 0. So then your thought is, okay, well, if it's add in between here, based on our last property we had, if I have the limit here and the limit here and it was plus there, I can just take those two limit values and add them together. So like the 3 and the 0, I can just add together. And that tells me my limit of that whole thing would be 3. Okay, and if you wanted to write it out in like the limit form, it would be like the limit as n approaches infinity of, and then you would write that whole original kind of function there. So 3n plus 2 over n, and then it just equals 3. If it doesn't say anything about writing it in that limit notation, you don't have to, but either of those would be fine. Okay? Okay, so that's that one, and then let's jump back to our normal number 1 example. Like I said, we're going to have to kind of jump around a little bit because when I was making copies of this, I didn't plan it out very well. Okay, so now we'll go to our normal example 1. So it wants us to find the limit of the sequence S, beginning with, and then it lists out some of those sequence values there, but it also gives us just that actual sequence there. So I'm just going to find the limit of this one. So I'm just going to start with my S sub n is equal to my n over 2n plus 1. And then what I'm going to do here is, this gets a little bit tricky, but what I'm going to do is I'm going to divide each of my values by n to kind of make some stuff go away, because as long as I'm dividing every single term in my thing by the same thing, it'll still kick out the same answer. So what I'm going to do here, I'll do it in a different color so you can kind of see it. I'm going to take this fraction here, I'm going to take the top and divide by n, so like n divided by n, and then I'm going to take both of the bottom things and divide them by n. Divide by n, divide by n, and again, that won't change our value at all because we're dividing everything by the same thing. We're just doing that so we're manipulating it in a way that kind of works out a little bit better for us. Then what's going to happen there is when we take all of those things and divide by n divided by n will cancel out to 1. Here we'd have 2n divided by n, so those n's will go away and just get us down to 2. And then here we still have this 1 over n. And then what you can think here, isn't this the same harmonic limit thing, or the harmonic sequence thing we had before, 1 divided by that value? So if it's 1 divided by that value, that means the limit of that's got to be 0, right? So here, if we switch it to limits, then we've got 1 and the 2, and that would be kind of like our constants. And if that one's 0, it would just be the same as like 1 over 2 plus 0, thinking like limit-wise, it doesn't equal that, but we're just thinking about limits. And then there, if that is approaching 0, we can just take that constant value plus that 0 value, and it's the same as a half. So that graph would end up approaching a half. So how we would write this out, you could either leave it like that, or like I said, if you want to put it in that limit form, it would be the limit as n approaches infinity of that original equation, or whatever it is, their sequence. And then that'll kick out a half. So either one of those would be fine as long as you can get to a half. That one's a much more complicated one. That's why I added that 1a in there, so we have a little bit less complicated ones. And like I said, when I put them on the test, I'm making sure they're ones that aren't too crazy. Okay, so there's another thing on that same packet sheet that we had here before with properties of limits and operations on sequences. So these are just some other things that you can do with this. So like this one was just solely focusing on if we had a constant value that we were adding or multiplying by or whatever. Now they're going to do it where you're finding the limit of two separate things and then either adding them, subtracting them, multiplying them, or dividing them. The only thing that you got to be careful on here is both of our sequences have to be convergent. So you can only do this when they actually approach a number. You can't do this if it's like, approaches infinity or negative infinity or like limit does not exist. Okay, you can only do this when they're convergent ones. Okay. So now we'll jump around to our sheets again here. We'll go to 2a, which is our one here. So what I would do on this one is kind of same as what we were doing on some of those previous ones there. So we got a couple limits that we're figuring out here, and then once we find those limits, they're both probably going to be convergent for us to be able to do this. We're going to multiply those together, okay? So here, if we're trying to figure out our limit as p sub n approaches infinity, we're using this guy up here, the 7n plus 1 divided by n. So there I would probably go, and I'll just do it off to the side here. I would take that 7n plus 1 divided by n. And it's kind of similar to the one we did up here, where both of them can be then split up into be divided by n. So you could split it as 7n over n and 1 over n. And then similar to before, well, if that's n and that's n, those can cancel, right? So that would give us like 7 plus, and then here that would be 1 over n. And then if we're thinking limits-wise, our limit of if it's just a constant number is always just whatever that constant is, right? So it would be like the limit as n approaches infinity. If it's just that 7, I'm just going to do it all as 1. So if it was like the 7 plus 1 over n, that would be 7. And then that 1 over n is that same harmonic one, so that would be 0. And then all we would have to do here is we would just add those values together. So 7 and 0 would just make that 7. Okay, so that's kind of similar to what we were doing on the 1a example. Then you'll just do that same thing for your q sub n. So you got 4 n plus 3 over n. And then you can just do the same thing. 4n divided by n plus 3 divided by n. Same thing will happen. N's can go away there. So then that'll leave us with 4 plus 3 over n. And then again, when you're thinking about the limits of that, so the limit of 4 plus 3 over n as that approaches infinity, I forgot my infinity up there, as that approaches infinity, again, if it's the constant value, it's just whatever that value is, so 4. And then here, again, it's not a 1 on top, but our bottom still could not be 0 there, so the limit of that would still be 0. And then we just add those guys together, so 4 and 0 would make 4. And then now this is where that new property that was that one we were just looking at comes into play. So because these are both convergent series, so they both go down to a number, if we just want to know the limit of both of those things, so the p sub n and the q sub n multiplied together, you just take both of those limit values and multiply them. So you would just take 7 times 4, which would give you 28. Okay? And that's a better example than, so the next one we're going to do here is the, well, I guess we're going to skip one and then go back to it. There's one in the book, or that came with the like normal example sheet that's like this, but they both do not exist, so it's kind of annoying that they even set it up like that, but we'll get to that one in a sec. The next thing I'm going to have us jump to is that other sheet. Everybody got another sheet that says like limits cheat sheet or something on it? This thing? Okay, So this one, basically the guy that I watch all his videos or whatever to kind of figure out like what's going on with the lessons or whatever, he kind of talked through the limits in a little bit different way that I thought made a lot of sense for certain situations. So he kind of broke it down into 3 different things here. You guys know numerator and denominator, right? Numerator's top of the fraction, denominator's bottom. So he kind of broke it down into how the numerator and denominator compare of these fractions as an easier way to do these limits. So what he's got here, and I would highlight this or do something to kind of star it. If your degree, so I'm going to highlight degree, and your numerator matches the degree of the denominator, then you're going to divide the coefficients. Okay, so if you've got a situation where so degree is always the highest power, right? So if you look through there and you are looking for like your highest power, so like in this one, just singled ends, if those match each other, the top one and the bottom, that they're just basic ends there, what you can do is you can just take your leading coefficients and divide them. Okay, so like here, why we can do this is because that one and that one have the same power. So if those have the same power and they're the biggest, powers there, what you can do is you can just take, so leading coefficients are just these front ones here, you can just take them and divide them. So you can just take -8 divided by 12, and that would reduce down, you can pull 4 out of each of them, so like -2/3, and -2/3 is your limit. Okay, same would work on like this next situation here. There's a whole bunch of stuff going on, but what we can do there is we can see, okay, our biggest power there is power of 2, biggest power there is power of 2. So if those match each other, we can just take those front ones and divide them. So our front one there would be 4, front one there is 12. So you can just take 4 and divide it by 12. 4 divided by 12, well, you can pull 4 out of each. So that'd reduce down to 1/3. So 1/3 is the limit. And then same thing on the last one. He just had 3 examples on his, so I just used his same 3 examples. So if that's n to the power of 3, again, that's the highest power. We can only do it when we're looking at the highest power. If those match each other, we can go, okay, well, leading coefficient there is 7, leading one there is 7. So 7/7 would reduce down to 1, and the limit of that one would be 1. Okay, so that's a little bit easier way to do it when it's kind of set up like that. So that's when they match each other. The next one is when the degree of the numerator, so I'm going to highlight again here, degree, numerator, this time is smaller than the degree of the denominator. The limit is always going to be, no matter what, 0. Okay, so if you've got something set up like one of these again, you're looking at your highest powers again for the degree of it. Here you've got n to the second is the highest one. Here you've got n to the third is the highest one. So there my numerator power is 2, my denominator power is 3. So because the top one is smaller than the bottom one, no matter what, this will always just straight up approach 0. Okay, so if it's ever set up like that as these polynomials, the smaller ones on the top, it will always, no matter what, approach 0. Okay, and there's more to it than that, but I'm just, like I said, this is kind of a cheat sheet to kind of break it down basic for you because I don't think we need to go super in depth into this stuff. Okay. All right, and then the last example here is when our numerator is the bigger one. So I'd go degree, numerator's larger than the degree of the denominator. On these ones, it's always going to be limit does not exist. In a finite sense, technically, like we were kind of talking about before, technically it can either go to infinity or negative infinity as well, but we're not going to get too crazy into that stuff, okay? So if you get a situation like this, where when we're looking at our powers here, you get n to the third and n to the second, if the bigger one is on top, it would just be, should be a D first, does not exist, or technically, in this case, it approaches infinity. But like I said, I would just go with does not exist because that's what the book wants. But technically, when you get to like other maths, if you're doing other maths out, technically it's infinity. But like I said, I would just go with does not exist. Okay, and hopefully that'll kind of ease our process here. So now let's go back to, I know we're jumping around a lot. Let's go back to our normal. So we got 2, regular number 2. So we're going to go normal example packet number 2. It's not even that packet. There we go. Okay, so this is the one that is kind of like the 2a that we did here, but like I said, I don't like this one as much because the part A's of it actually don't approach, infinity, or they don't converge, so we can't even use the special properties things. So I'm not actually going to worry about figuring out the properties of either of those. If you did have to figure out the properties of either of those, I would probably actually just graph it and see what they approach. They both actually approach infinity, so they don't work under the special like convergent rule or whatever that we just wrote down. But what I would do here is I would use that cheat sheet method that we just came up with here, and I would just rewrite this. So again, I'm just going to kind of skip A there because it's not super important to us. I'm just going to do B as trying to find the limit at, oops, I don't know why I put a line there, ignore that line, as n approaches infinity. And then here, instead of writing it out as like u sub n and v sub n, I'm just going to put those actual things in there because then it'll be set up like we were just working on. So like my u sub n is 4n squared minus 1 over 8n squared plus 20n plus 5. And then if we're just trying to find the power, or not the power, the limit of something like that, we can just look at our powers. So like there, if that says n to the power of 2, and the highest one there is n to the power of 2, well, those would be the same. So I would go back here to my one where it's the same, and if my numerator matches, I'm going to divide my coefficients. So here, my numerator and my denominator match for our powers, so I'm just going to take and I'm going to divide the coefficients. So it'd be like 8 over 4. And we know 8 over 4 would reduce down to a half. So that would end up being a half. And again, that they're asking a little bit goofy stuff with that A there, so just don't worry about that. But okay, so let's do one more here, and it's on the extra little sheet thing. It's on this guy. If you do have a situation like this where they're asking you like something like this and you're trying to figure out what happens as you approach infinity, also, if you notice here, I switched it from x's to, or from n's to x's. That doesn't matter. But here, what I would do if it asks a question like this, and I don't think I think there might be one of these on the worksheet, is why I threw this example on here. But I don't think I put any like this on the test. If I was trying to find this limit as it approaches infinity, what I would do is I would graph it. So I would just graph like x to the power of 3 plus 2x plus 1. Hit graph there. And you get something like that. So we know with our powers of 3, it's kind of like those odd shape graphs where it's kind of like rotation symmetric or whatever. So if I'm thinking here, as my x approaches infinity, so as I work my way to the right, what's going to keep happening with that line there? Is it going to converge at anything, or is it just going to keep going up forever? Probably just going to keep going up forever, right? So what I would do in a situation like this is another one where it's like, okay, it doesn't converge or whatever. So what you can do is you can just say, like, does not exist, or technically it does go to infinity. What I would do on this one is I would just sketch myself out a little graph, kind of like what we did, or what we just graphed there. So you can kind of see, like, okay, as I go, across to infinity here, what happens to my value? Well, it's not converging at anything, so it does not exist for a finite sense, or, goes to infinity. The other thought process on this is, if you wanted to think back to our cheat sheet, how this would kind of work, is if we had this as like x to the third plus 2x plus 1, it's not over anything, but it would kind of be like it's over x to the power of 0, because x to the power of 0 is the same as 1, and we can put anything over 1. Then if we're thinking about powers wise, well, that's a power of 3, that's a power of 0, bigger one's on the top. So if I'm looking at my cheat sheet, bigger one on the top also goes to does not exist. So you could also kind of think of it in that sense. Again, I think I just threw that one on there because there's one on the worksheet that's kind of like that, where it's not like a fraction. But like I said, when I made the test out, I made it ones that hopefully aren't too bad. Okay? Okay. I know that was a little bit, I don't know where our note sheet even is. I know that was a little bit all over the place, so hopefully you kind of at least got something out of that. But like I said, instead of doing a book page for this, I'm going to have us just do a worksheet on it. Did everybody get that worksheet from the other day? So it should look something like that. There's this side, and then there's this side here. It says 8.2 because in the old books it used to be section 8.2 instead of 8.3, but it's just from the old version of these books from 1992. But it's the same math. So I would do your best on that. I'll put the answer sheet up here so you can kind of check yourself as you're going, as long as I can find the answer sheet. But like I said, if there's stuff we need to talk through, feel free to ask questions or whatever.